Good morning, everyone. Welcome to our Zoom lecture. Before we get started, I just want to make one announcement. Next week on Thursday, June the 3rd, we will have our first midterm exam number one, scheduled for next week, Thursday, June the 3rd. I want by this coming Thursday, whatever we will cover on Thursday will be in the midterm exam. I would like to give you 1 week to study, prepare yourself for the exam, which means next week, Tuesday, material, whatever we will cover on Tuesday will not be in the exam. I will also use the Tuesday next week to probably maybe answer any question, address any concern you may have, so that when we meet on Thursday, you will be ready for the exam. All right, so Thursday, June the 3rd, will be our midterm exam number one. Take note of that. If you were not here last week, we finished chapter 2, and today I will start lecturing on chapter 3. Yes, Daniel, I'll give you the study guide for exam number one. I'll give you the study guide that you need to know this. You need to know this. I'll have that ready by Friday so that you have 1 week to do that. Yes, the exam will start from 10:30. 10:50. And based on the nature, we will only take the exam on Thursday. We'll take the exam on Thursday, and that will be it. I want you to really focus, not to come and expect a lecture. So it will start, not exactly 10, but be ready 10:50, because some folks might be joining in. Let's be safe. Around 10:55 is when it will kick on. More information with that regarding that will be shared on the announcement section. Uh, Tentatively, right now, I haven't looked at the question. The exam is not ready to really tell you I don't know how many questions, but I've seen in the past in the neighborhood of 40 to 50. I'll tell you how many questions will be in the exam along when I post a study guide. So be ready between 35 to 40. Precisely, I'll know exact number of questions by Friday. So I'll tell you how many questions, the nature of question, if it is filling in the blank or true and false. All right, just to be aware, 40 to 50.
Professor, is the exam going to be proctored through Zoom or is it going to be through Lockdown browser?
It's gonna be through lockdown browser.
Okay. So is it going to be at class schedule?
Yes,
Okay.
like 10:50, same time. It's not 24-hour window, but during the exam. Assume that this is face to face. You have got to show up in class and take the exam, so it's the same way.
Okay. Thank you.
All right.
Are we allowed to have scratch paper and everything?
Yes, you'll need a scratch paper. I'll give you any other material you may need, such as the periodic table. All right. The formula sheet, I'll give you that as well. If there's any equation you will need, or if there's any constant you will need after looking at that. All right. So Nikki is actually just bringing to your attention again that look at the SI for help session. There is a schedule for support system. Please check on the announcement if you need some help with that. just email Nick and he will get back with you. So without wasting my time, I want to just dive into chapter 3, which is pretty straightforward. It is a straightforward chapter, I believe, and I trust that you have mastered chapter 2. You need to be well-rounded with chapter 2. In particular, using the periodic table to predict the ionic charges, writing the correct formulas for ionic compounds, writing the correct formulas for molecular compounds, keeping track of, the polyatomic ions, the names, as well as their ionic charges. That is the foundation we will need to nail down chapter 3. It will compound if you think that you don't need the information or the concept we learned in chapter 2 regarding the writing the correct formulas, the ions, polyatomic ions, and predicting the ionic charges for monoatomic main group elements using the stock system, to write the ions formed by the transition or some of the transition metals with more than one charge. What does the Roman numeral indicate? It will be handy in chapter 3. That is the chemical reactions and reaction stoichiometry. We know what a reaction is. When you mix two reagents, reaction takes place. And chemistry use what we call chemical equation to represent a reaction. And coefficient in the, we cannot talk about that, indicates how many or quantitative relationship between the reactants and the product is what we call stoichiometry, comparing that. That's what we will be looking at in chapter 3. And here is the roadmap for chapter 3, all right, the outline. Section 3.1, we will look at the chemical equations. You should be able to interpret that. I know this was covered in introduction to chemistry. You know what a chemical equation is. It represents chemical reaction. The balancing of the equation. All right, balancing of the equation tailors on to chemical equation. Now, simple patterns of chemical reactivity. We'll talk about the decomposition reaction, combination reaction, all right, combustion reaction, and more will be covered in chapter 4, oxidation reaction. But I would like to just recommend that learn about six types of chemical reaction: combination reaction, decomposition reaction, single replacement reaction, double replacement reaction, combustion reaction. Section 3.3 formula weight. I know we covered this, finding the molar mass. Formula weights, wherever we are referring to ionic compounds, we talked about formula weight, adding the atomic masses of elements in a compound gives you what we call formula weight. Molecular weight is strictly referring to molecular compounds. It's the same thing. Avogadro's number, this is the numerical value used by chemists to represent certain number of items or things. I know you have seen this. 1 mole of equals 6.02 times 10 to 23 things. This is what we call Avogadro number. And chemists use the simple Na, the subscript capital A, for Avogadro number. And of course, where we are going with this, we will use the dimensional analysis we learn in chapter 2 to change between moles and particles, molecules and particles, and the molar mass, which we'll cover in 3.3. And then our empirical formulas, we look at the empirical, how to determine the empirical formula. I know we only talked briefly in chapter 1, simplifying the subscript in such a way that you end up with the simplest. But here, we will look at the analysis of compounds to derive the empirical as well as the molecular formula. And let's look at the a balanced equation and the concept of the limiting reagent does not mean that when you have two reagents, all of them will be consumed at the same time, that they will run out at the same time. If one reagent run out fast, that reaction is considered as limiting reagent, or in other words, a reagent which gives the least amount of the desired product is the limiting reactant in a chemical reaction. So if I look at these, the first four sections here, you can comprehend, it's not hard, maybe 3.5, 3.6, and 3.7 might be new to you. So let's see, what is the term stoichiometry? Stoichiometry is simply defined as quantitative, all right, quantitative relationship between reagents or reactants. All right, sometimes we call these reactants. The terms can be used interchangeably, and products in chemical reaction. In chemical reaction, we call just simply, the definition of stoichiometry is derived from the Greek term stoichion. All right, we're not going to look at that details, but just that is the quantitative relationship between product and the reagent. And we talked about the law of mass conservation in chapter 2, all right, during the development of the atom. And Antoine, who is credited for the law of mass conservation, used the stoichiometry. He was taking the mass of the reagent and comparing at the mass of the product, and every time he ended up with the same amount. So in other words, he was doing some sort of stoichiometry. That's why he's regarded as the father of the modern periodic table. I'm not gonna ask you, define or put down the words what he is credited for, or what he said in terms of the words you see in italic here. But take home point here is the stoichiometry. What he was doing, he was comparing the masses of reagents and the masses of the product, which is the stoichiometry, which is what we are basically doing in modern day. And if you think in 17th century, what he was doing and what we are doing right now, it's safe to say that, is the father of the modern chemistry. Now, so that is what we will be looking in chapter 3, product reagent. But before that, we should be able to interpret a chemical equation and what it represents in terms of chemical reaction. All right, chemical equation, you have seen this. Let me just use a generic. If I have aqueous plus B, I'm just writing some numbers, S going to, and I can put something here to produce C, and then I can have here liquid, all right, and then D, I can have gas right here. I'm just using some of the symbols you will come across, you will see in any chemical equation. Now, if we break down, you understand that what we have on the left side of the reaction are, these are reagents. We call these reagents. And this means, right here, means A is reacted with B. Addition, it's not like mass that the 1 plus 1 is 2, but with respect to chemical equation, addition means A combines with B, A react with B, all right? Those are or what plus means. The arrow here can mean produce. That means A and P produce C and D. It can also mean yield, all right? It can also mean give or to give. Reason why you need to know this is you will be given with the water equation and how do you interpret or translate to chemical formulas, and then you balance the equation and probably calculate the theoretical yield, which we are going to talk about later. And then of course to produce C and D, these are the products. We call these products. All right. What you don't see here is I can have a number here. I'm just putting some hypothetical numbers. We call this coefficient in the balanced equation. We're gonna talk about that. So in brief, you know this what I just demonstrated on the whiteboard, what it represents. The subscript here indicate the physical states of the reagent. What does the physical state? This means aqueous. You know what aqueous is? Means dissolved in water. AQ here, AQ like that means aqueous, which means dissolved. All right, dissolved in H2O, in H2O. So I can have this. That is sodium chloride, right? And even I can add this, it means in solid state. But I can have this NaCl and then subscript right here. This means salt, salt solution. And table salt sodium chloride has been dissolved in H2O. So here means aqueous. And of course, S means solid, L means liquid, and G, and of course, the cathode in parentheses mean they are in gaseous state. It's breaking down the, what those symbols are. In the exam, I'll ask you what does addition means, what does, where are the product or identify the product in the following, to show that or to see if you are able to interpret a chemical equation. Now, something I didn't explain here is, I almost forget, is what are these uh, delta sign above a chemical reaction? It means heat is required. If you see something like this, an arrow with a delta sign like this means heat is required for the chemical reaction to take place. That means heat is required for chemical reaction to take place. You may see something also like this with maybe an element above it. You may see something like that above it. This means a catalyst. You know, a catalyst, a species which speed up the chemical reaction but does not participate in the formation of the product. So in this case, if we had a reaction, we know iron is required to catalyze the reaction. Palladium, Pd, is required to catalyze the reaction. So having said that, product reagent, you know where they are, just to bring to your attention what where the products and reagents are in a chemical reaction. So here are products. Addition means, A and B react to form C and D. Later on, we will look at the balancing the equation. The two here is the coefficient required to do it to balance the equation, All right. Yes, Price. I'll just get back with you. I got your message regarding quiz number 2. Yes, quiz 2 is not only crucial for upcoming exam, but it is crucial in mastering chem let's put it this way. Mastering chemistry, chapter 2 is crucial. Because why? Periodic table is like the letters of alphabet. A through C. You can recite that A, B, C, D, but out of that, a lot of novels have been written. People have, they can tell stories and stories. So likewise, if you nail down chapter 2, I think you will have mastered the course. Thank you. I'll come back to that. So if you look at yes, there'll be some, Daniel, there'll be some, not, I cannot promise like, study the quiz, but it's the same concept that if I know it, I know it. Let me give you an example what I mean by understanding the concept using the crossover rule. If I know the ionic charge for sodium, I know the ionic charge for oxide, and I can write the word, use the crossover rule. So you may not really see one-on-one, word by word, question by question from the problem, but it is about the concept. If I know the prefixes used to indicate how many atoms of nitrogen, how many atoms of oxygen, nitrogen dioxide, all the prefixes, no matter what I'm given, and I know that they are non-metals, nobody will trick me. So it's about the concept. It's not going to be word by word that let me memorize all the questions on quiz 2, let me memorize all the questions in quiz 1. It's about the concept. So just to point to you, you may see, but I would recommend that mastering the concept is the key. All right. It's just like, let me give you an example, open book, right? I'm not saying that I'll give you an open book exam, but if it was in class and then you don't study, you say, I'm gonna study in the class, open book, but if you look at the example, it has nothing to do with the actual question in the exam because you don't know the concept. So hope that answered your question, Danielle. Hope that answered your question about the question on the exam. We'll come back to that probably next Tuesday once you have the study guide and once you have, maybe, I don't know if I'll be done with chapter 3 to make the quiz available. So back to the equation, you need to know what addition means, a separate product from the reagent. I use these numbers and just brought to your attention that they represent coefficients. Coefficients are numbers used to balance the equation. And balancing the equation is making sure that the atoms on either side of the reaction are the same. Atoms of on either side yes, Caroline, if you'll have any question about the study guide, once I make it available, just come to office hour. You can go to SI session for support. You can email me if I'm available. I can help you one-on-one on any specific question you may have or go over again some of the concepts you may need some revision. For example, if you need some help with finding the molar mass of, then I can help you with that. Or you want to know how to write the chemical formula of a compound, how do I go about this? I'll be more than happy to help you with that during the office hour, or you can go to a SI session. The hours are available on Canvas. Please take note of that. Or you can email me if none of those really fit your schedule. I'll see if I'm available to help you one-on-one over Zoom. So with that, all right. Yes, Nathan, if that is the case, I'll make that, I'll extend that for you, all right? We'll come back to that later at the end of the session. Let's just move this for quiz 2. I'll come back to that. And it's your exam. I'll take into account that. Thank you for bringing that to my attention about quiz 2. Now, balancing the equation is just making sure that the atoms on either side of the reaction arrows are the same. Because of why do we have to balance the equation? Because of the law of mass conservation, which we learned earlier on, which goes back all the way to 17th century. And the law of mass conservation states that matter cannot be created or destroyed. And let's say if hydrogen gas react with oxygen gas to produce uh, liquid H2O here, the equation is not balanced. Just to give you the sense of balancing the equation, in the sense that the number of hydrogens, yes, it's balanced out. We have two hydrogens here, two hydrogens, two hydrogen, and by the way, our point of reference is the arrow. That is what we are comparing. I don't see any other hydrogen on this side. I don't see any other hydrogen. So the hydrogens. The problem now is oxygens. We have two oxygen on the product side. We have one oxygen on the product side. Reagent side, we have two oxygens. Let me just put these oxygens and then oxygen right there. So how do we make the number of oxygen the same? Is by using what we call coefficient, Never balance the equation by changing the subscript. In other words, you cannot just put a subscript there and you say the equation is balanced. That means you are changing the chemical compound. Never balance the equation by changing the subscript. The only way to balance the equation is use a coefficient which goes in front of a reagent, and this applies to both hydrogens and one oxygen. You read this as what? 4 hydrogen, 2 times 2 is 4, 2 times 1 is 2. So we have 2 hydrogens here, 2 oxygens, but the number of hydrogen has changed to 4. So how do we make the number of hydrogens the same? It's by just placing the 2 here. When there is nothing in front of a reagent or a product, it is understood to be 1. You cannot say 0. Nope. I've seen some questions on balancing the equation saying that when the following equation is balanced, what is the coefficient of oxygen? And somebody will say 0 because they don't see anything. You never balance the equation by putting 0. It's gonna make everything 0. So when there is nothing in front, it is understood to be 1. I've seen question on balancing the equation again along this line. When the following equation is balanced, what is the sum of the coefficient? What is the sum of the coefficient? So if I look at this one, the example on the whiteboard, somebody will add 2 plus 2 and they say 4, and then they see on the multiple choice and then they pick that and they end up at here is 2 plus 1 plus 2, 5. So it still revolve around balancing the equation, So this is a reason why we balance the equation. You need to understand that question also could be, why do we have to balance the equation? You may not have, or you didn't have the answer, but moving forward, you need to understand that balancing the equation is essentially in observing the law of mass conservation, that we do not destroy. Otherwise, if we live just the way we have this, it will just mean that we are destroying oxygen. We are missing one oxygen. So that is as simple as that in terms of balancing the equation, that the coefficient applied to both. Now, suppose we have, let me just show you, suppose we have a subscript such as, let's say this right here. I'm just making it hypothetical and say, let's say you are balance the equation and a coefficient of 2 goes in front of calcium hydroxide. I want to show you how the coefficient and the subscript changes the number of atoms. This means you have 2 calcium, you open these 2 times, look at these 2 times 1 oxygen here, we have 2, so you say 2 times 2 oxygens, all right, this subscript right here, and then times 2, all right, 2 times 1, it's 1, 2 times 1 oxygen 2, so here we have 4 oxygens, we have 4 oxygens. That's what the subscript means. 2 times 1 times 4, we also have 4 hydrogens, 4 hydrogens. So you balance the equation. Never change the coefficient. Never change the coefficient. I mean the subscript. Never change the subscript, but use the coefficient. I mentioned about what 1 means. If there is nothing, it's understood to be 1. Do not change the subscript. If you change, you'll end up with something different. Maybe you are intending to mean H2O, but if you change, you'll end up with hydrogen peroxide, which is totally different compound. So it's simple as that. I know it's with practice that you will, all right, you will master the balancing the equation. Any question on, any question? Oh, I explain what the symbols are. Symbols are the subscript, or, you know, what we have in parentheses. This means it is in gaseous state, you know, we can have liquid state, we can have aqueous. I explained that the chemicals or the states. States mean solid, liquid, gas, and of course the aqueous. Question on this understanding: when this is used in a chemical equation, what does it mean? It means gas. When this one is used, it means liquid. When this one is used, it means solid. We use that. Aqueous means dissolved in water. A solution as a solution where H2O is used to dissolve a solute, you end up with aqueous solution, aqueous solution. Delta symbol above a chemical reaction arrow means the heat is required. You need to heat the reaction. Methane, oxygen to produce liquid H2 and carbon dioxide, we need heat. Otherwise, the two will just will not form the products. Will not form the products. Here is an example on balancing the equation, and I had to give you an example of the worded chemical equation and a chemical equation with chemical formulas. And when it is in this form, it is pretty straightforward just to, you know, plug some numbers and see if it is going to work out. If it does, and then you have yourself the balanced equation. So here is oxygen gas reacting with carbon monoxide to form carbon dioxide gas. So the way you go about with this is you look at the atoms on either side. You look at the atoms on either side. We have one carbon, we have one carbon. You can use a check mark, all right? Let carbon is balanced, but the number of oxygens, we have what? Here is 2 plus 1, 3 oxygen on the reactant side, and 2 oxygen on the product side. The equation is not balanced. The equation is not balanced. We need to balance the equation. We need to balance the equation by using the coefficient. So let's say if I use 2 here, the number of oxygen will change to 4. So here I will have 4 oxygens because of 2 times 1 is 2 plus 2. You read this as 1 times 2, 2 plus 2 is 4. On this side, I do have 2 oxygens. So what do I need to multiply by 2 to make 4? This will be 2 what? 2 as a coefficient, and we have now 4 what? 4 oxygen. So oxygens, the way it is right now, is balanced. We say it's balanced. That's balanced. That's balanced. 2 carbons and 2 carbons. So these are the coefficient. You may want just to put one right there for, even though it's understood to P1, we say the equation is balanced. Equation is balanced using trial and error. There is no formula that you can plug and play and say this is what it is. So for B, aluminum carbide react with water to form aluminum hydroxide solid plus methane. Here we have 4 what? We have 4 carbons. Let me see if I can use 4 here. Just to balance the high aluminum 4. So 4 aluminum, 4 aluminum. Let's see, carbon here we have 3. I have here 1. So suppose we put 3 here to balance the number of carbons. It's just using trial and error. I don't know if it's going to work. So aluminum and carbons, they are taken care of, but now the number of hydrogen, let's see hydrogen. We have 2 here. The number of hydrogen here is 3 times 1 is 3 times what? Times 4, that is 12. So we have 12 hydrogens. That's not the end of the story. We have 12 here. And here we have what? We have 12. You see 12 times, 3 times 4 is 12. So in total, we have 24 hydrogens on the product side. So what do we need to multiply by 2 on the reactant side to make 24? That means we need what? We need 12 here to make 24 hydrogens. Hydrogens on the product side, 24, hydrogen on the reactant side, 24. Let's make sure that the oxygens do add up. 12 oxygens on the reactant side. If you look at the product side, this is 3 times 1, that's 3 oxygen times 4, 12. So 12 oxygen, and the equation is balanced the way it is. So we have 1 right there, we have 12, we have 4, we have 3. The equation is balanced. It's just trial and error, all right? It's trial and error that you end up with a correct coefficient in the balanced equation. That's what you need to know. Now, let me clear this, and I'm just going to clear the drawings, all right? Now, see example, see here, this is an example on worded chemical equation you are expected. And this is what I raised in chapter 2, that when we get to 3, you will be expected to be proficient in writing the formulas of the compound, whether it's molecular or ionic compound. You are expected also to know the chemical symbols of element of the periodic table. So solid zinc, so that means what you need to write is zinc, solid, it's in solid state. React with, remember react with from what we just went through means addition. Sulfuric acid. And all acids, you are expected to know the formula for sulfuric acid. This is chapter 2. And all acids are aqueous. That is the formula for sulfuric acid. To form, that means you need to write, draw an arrow. That means to produce, to form, to give, to yield. Hydrogen gas, there were 7 diatomic elements on the periodic table I gave you. It's in chapter 2. Diatomic, most gases except group 8 gases are diatomic. Hydrogen gas is diatomic. Oxygen gas, because you're gonna see this, oxygen gas, nitrogen gas, fluorine gas, chlorine gas, bromine liquid, all right, and then molecular iodine, which is liquid. Those are diatomic compounds, which we covered in chapter 2. So remember this. So this means hydrogen gas, it is not H alone, it's H2 subscript, it's gaseous. An aqueous solution of zinc sulfate using group 2, or rather polyatomic ion zinc has a positive 2, and you need to know the formula for sulfate. This is not sulfide, but sulfate. Where I'm going with this is to write the formula for zinc sulfate. Take note that I didn't memorize the formula for zinc sulfate. There is no way you will memorize formulas for all ionic compounds. There is no way you will memorize all formulas for molecular. It does. You're just making your life complicated. I'm using the crossover rule, understanding that the ionic charge. Here is the deal. You need to know the ionic charge for polyatomic ion, so that zinc sulfate will look like this, and it is aqueous solution, so that means it's AQ. With that, I'll just have to write the formula for zinc sulfate. That's not the end of the story. We need to balance the equation. And stands out that by just inspection, it looks like the equation is balanced. One zinc, we have one zinc on the product side, two hydrogen on the product side. You can balance polyatomic ion as if it is a single entity. If it does not change, you don't need to break down as sulfur oxygen. If it is just sulfate on the reactant side, sulfate on the product side, you can balance as a single entity. That's what I wanted to just show you how to go about with balancing the equation. This illustrates that you may be presented with chemical formulas of reagent and product, and you are asked to balance. Or another scenario is you will be given awarded chemical equation. You are expected to translate chemical formulas, chemical names to chemical formulas and balance the equation. Take note of this. If you didn't know how to write the formula for sulfuric acid, then you will not balance the equation. If you don't know the ionic charges or how to use the crossover rule, then it's gonna be difficult for you. Yes, I'll give you the periodic table. Lauren, I'll give you the periodic table. But during the homework assignment, you can use any periodic table. Yes, I'll give you the periodic table during the exam. Thank you. So that's balancing the equation. Any question on balancing the equation? Any question? Please use end of chapter problems, the odd numbered problems at the end of the chapter has solution at the back. You can practice with that. Let's move on to the simple patterns of chemical reaction. And a simple pattern is nothing different from what you have covered in the lab. What do I mean by that? Types of chemical reaction. There is the combination reaction, which means from the word combine, two or more substances react to form one. From the word combine, all right, just to give you practice with the physical state. From the word combine, that means you are putting them together. A and B combine to form C. There is the decomposition reaction, which means one breaks down into simpler. This is an example of decomposition. To decompose is to break down B plus C. One is breaking down to form simpler compounds. Combustion reaction, from the word combustion, means reacting with oxygen. Okay, these are the three types highlighted in the text. I want you also to copy on this and learn double replacement reaction, how to look like, switching the cations, single replacement reaction discovered, acid-base neutralization is a special type of metathesis reaction or double replacement reaction. And we will look at the redox reaction in chapter 4. We're gonna look at the redox reaction in chapter 4, where we keep track of electrons. We keep track of electrons. So here is an just simple, two simple examples of combination reaction. At this point, you are expected to balance the equation. We do not only write that A and B without, we have also to factor in that the equation should be balanced. Equation should be balanced. From chapter 2, we learn how to write the correct formulas of ionic compound involving polyatomic ions, crossover rule, calcium hydroxide. Nevertheless, you should be able to see this. So one question or a question could come along this line: classify the following chemical reaction. Or how will you classify this? And then if you know that two or more are combining to form one, then you classify that as combination reaction. Combination reaction. Combination reaction prediction. Prediction. How do you know that this is the correct formula for your final product? Which means if A is a metal and B is a non-metal, I've highlighted this by the fact that you should be able now to predict the ionic charge of metals. Group 1 form positive 1. Group 2A form positive 2. The most common ionic, the positive 3 in group 3A is aluminum. That's the most common one you will see. And then group 4 also consists of non-metals. They are metalloids, and then there are metals. You got to be careful now on how you read that. And then you move on to non-metal. With that, you should be able to write the correct formula for your desired product, predicting the desired product. Here we are given magnesium, magnesium reacting with oxygen, and remember, oxygen is diatomic, so we expect to see this. Somebody might just say, if it is combining, why can't I just put it this way? And then I see a lot of students doing that. You have to play by the rules. It does not mean you slam them together and then say you have your compound. No. It doesn't work like that. You have to use, predict the ionic charge. So this is wrong. You have to ask yourself, this is group 2 combining with a non-metal or oxide, crossover rule, you bring down that, you bring down that, and what you'll end up with is, this is the formula for magnesium oxide. Remember, we simplified. There is magnesium oxide, because if I bring 2 here, you end up with Mg2O2. I still need to simplify pi 2. And that will cancel. That is the correct formula. But you have the right formula for your desired product in this example, but the equation is not balanced. You are breaking the law of mass conservation. All the time, we need to observe that law, which means we got to make sure that the number of oxygens adds up on either side. And the only way we can do that is to have a coefficient 2, and it applies to magnesium. And oxygen. So I read that as 2 magnesium and 2 oxygen. The oxygens are 2, so I need to put a 2 in front of magnesium, and I need a 1 right there. So 2 things, or simultaneously writing the correct formula, balancing the equation. This applies to any non-metal and a non-metal that you need to remember. For those metals which form more than one charge, the stock system will give you a hint on the ionic charge of the metal, such as iron 2, iron 3, copper 1, copper 2, and then you take it from there to balance the equation. So we can predict the formula for ionic formula for ionic compound. I see on page 112, all right? There are a couple of questions, regarding combination reaction. And they are worded chemical equation, and then just regular equation with presented with chemical formulas. You need to be able to balance the equation, for that. The decomposition reaction, maybe before we look at the decomposition reaction, I can look at one example in the text. How do we, even though I've used that, there's a problem on page, on the combination reaction. Combination reaction. Aluminum react with chlorine gas, for example. What is the product? This is the combination. Of course, you'll not be given just a question like that, but aluminum combined to form aluminum chloride, or here in conjunction with that, you're expected to know that aluminum is in group 3, form positive 3. Chlorine is in group 7 with an overall charge of negative 1. So we do the crossover rule. What we will end up with is the product here is aluminum chloride. We play by the rules. Don't just put them together like this. No, don't think that you just put them like you're combining. I'm playing with the rule of crossover rule. When a metal combined with a non-metal, what is the atomic charge for my metal? What is the atomic charge for non-metal? And then I write the correct formula for with the product. Then from there, you balance the equation. This is a combination reaction. So if I look at the reactant and product, 2 chlorines and 3 chlorines, you need a coefficient here to balance the equation. 2 there, so 2 aluminums, 6 chlorine, that means we need a 3 there to make chlorines balance. The number of aluminums different, we need to put that 2 in from right there to give you a balanced equation for combination reaction. Maybe you'll see this if you are taking the lecture, one more example of magnesium plus nitrogen gas. You'll see this in combustion reaction, right? You've seen combustion reaction experiment. What is it? Somebody might think that you put them together like that and you have yourself the desired product. We don't need that. That is wrong. You need to ask yourself, what is the ionic charge for magnesium? It is in group 2. What is the ionic charge of nitrogen? It is in group 5. It has an overall charge of -3. Then use the crossover rule. This will come down. This product here is Mg3 is coming from nitrate, and the 2 here is coming from magnesium. So the product here is Mg3 and 2 and 2. That is magnesium nitride. When you burn, or you will see it's online lab you are doing right now, there is a simulation where the instructor is burning magnesium, and then later on you add deionized water to convert magnesium nitride, which you see as the product here, magnesium oxide inside that. So having written down the correct formula for the product, so overall, you need to balance the equation. So if we put a 2 here in front of magnesium nitride, we have 6 magnesiums. We have 1 here, that means we need a 6 in front of magnesium there. 4 nitrogen to something here we need to simplify. If I can still simplify by 2, that means I'm gonna need a 3 here. All right, I need a 3 here. I need a 1, so that means it's gonna be like this. We don't need anything here. So, and this will just be like that. This is an R. So it's 1, 1 like that. Nitrogen, magnesium react with that. I simplify. I add 6. 2, 2. You can see simplify 3, 1, 1, which is the lowest. So don't just leave it. If you can still simplify, sometimes you may end up with similar situation. You got to break it down. Any question on combination reaction? This is maths. You need to practice. Let's move on to second type of second pattern of chemical reaction. Decomposition reaction is breaking down one compound to two or more. Here is an illustration of, the sodium acide. What is happening here is inside the air bag, we have sodium what? Sodium acide breaking down to sodium plus nitrogen gas. This is nitrogen gas. This is responsible, nitrogen gas is responsible for inflating the air bag. And this one is breaking down to simpler substances. So if we put a 2 there, and a 3 there, we end up with a balanced equation. Sodium solid and the gas right there, gas. Decomposition reaction, breaking down to simpler compounds, sodium chlorate, lead 2 carbonate. This is lead 2 carbonate from lead 2 oxide and carbon dioxide gas. Copper, this is copper 2 hydroxide. There is copper 1 hydroxide. There is copper 2 hydroxide, breaking down to copper 2 oxide and calcium H2O, calcium H2O. There is lead, all right? Let me just highlight how you can predict which one you are dealing with. Carbonate is always negative what? Negative 2, this is carbonate, all right? But lead, we have lead 2, and then we have lead 4. If I look at the formula here, the 2 you see here, cancel out with the 2 here, this is lead 2. There is copper 1, all right? We know oxygen is always negative 2 oxide. There is copper 1, and then there is copper 2. If I look at this formula here, this has canceled out the 2 and the 2 from oxide. Always oxide will have an overall charge of negative 2. So it has canceled out from this. So this is copper what? Copper 2 oxide, copper, but nevertheless, the point here is breaking down to simpler substances. What I want you to focus is the decomposition of metal carbonate, and there is metal hydroxide, that is metal hydroxide, and there is the metal carbonate like that. You need to know which metal you are referring to, and then the carbonate. Let's look at the metal carbonate. What do we mean by metal carbonate? What is that? This metal part coils down to which group is that metal, and then the carbonate, of course. Calcium is a metal, and then calcium carbonate. This is what you need to know. Okay. How do I write down the metal carbonate? The metal carbonate will always break down to produce metal oxide plus CO2. The common product is CO2 gas. You'll always see CO2. So you'll always see CO2. But the metal here will vary from metal to metal, which group does the metal fall into. So here, if it is breaking down, if I have calcium carbonate, for example, that is the solid, is breaking down, maybe we are heating. That means heating calcium oxide plus CO2. And remember to balance the equation. CO2 is gaseous, this is solid, oxide is solid. Ask yourself, is the equation balanced? One calcium, one calcium, one carbon, one carbon. Three oxygens, we have one plus, so the equation is balanced the way it is. One. The point here is the metal oxide, this metal oxide and carbon dioxide is common in all of them. It will not always follow that pattern that, just always put the element and then the oxide. I can give you an example like this, aluminum carbonate, maybe even somebody will write that and then say it's gonna form aluminum, aluminum oxide plus CO2. It does not work this way. Somebody saying that, why don't I just put the way you did in calcium? No, it is about the metal. Look at here, metal, which group it is. So to start off with, this is wrong. You need to write the correct formula. You need to write the correct formula for aluminum is in group 3. So the 3 will form, and remember to use the parentheses. Remember to use the parentheses for this carbonate and then the 3 there. That is calcium carbonate. Maybe to be more visible, I can have this. This is carbonate, and then I use parentheses right there. What am I ending up with that? Aluminum, of course, and then the carbonate like that as an overall charge from polyatomic ion, and then I cross over. Now, if you look at the oxide as well, aluminum oxide will be Al is aluminum is group 3, and then oxide. So the desired product here is Al2 is coming from oxygen. We don't need the parentheses, but we just put the 3 here. That is the aluminum oxide. The metal here, the ionic charge for the metal will vary from group to group. Plus carbon dioxide, of course. It is always for metal oxide. Aluminum is balanced out. Carbon is, we have 3 carbons on the reagent side. So if we put a 3 here, if we put a 3 in front of carbon dioxide, means we have 3 times 1 is 3, 3 times 1 is 3. So carbons are taken care of. If I look at the oxygens, 3 times 3 is 9. 3 times 3 is 9. On the product side, 3 times 2 is 6 plus 3, so it's 9. The equation is balanced the way it is, so the coefficient here is 1, 1, and the equation is balanced. I want you to take note of metal oxide here, that metal oxide being referred to here is, it depends on which group number. It depends on which group number you are referring to. So that is what it is. Using the periodic table, you can predict the ionic charge. So metal carbonate. Balancing this equation is also, you saw how I was balancing the equation for carbonate. I had to balance the equation. It was 1-to-1, not always 1-to-1. There is a balancing the equation, for example, in there. The composition reaction, balance the equation. So always metal oxide. Give off carbon dioxide and a metal oxide. Those means heating. You need to burn. Every reaction on decomposition. Now for this one, I just to give you, even though it's not, you need to understand what metal hydroxide. Metal hydroxide will always produce no, hydrogen carbonate. I meant to say here metal hydrogen carbonate. Remember, hydrogen carbonate is a polyatomic ion, HCO3 with that, like that. This will always produce metal carbonate plus H2O, which is common, liquid H2O, plus CO2, which is gas, metal hydrogen carbonate. So metal hydrogen carbonate, which metal are you referring to? Which metal are you referring to? Is it group 1? Is it group 2? Let's see. In comparison to that, I can have here calcium hydrogen carbonate like that. Remember, calcium is in group 2, or even rather this, let's say potassium hydrogen carbonate. Potassium hydrogen carbonate. This is a solid. So this will give us metal carbonate plus H2O, which is water liquid, plus CO2. So we write the equation for that. Calcium hydrogen carbonate, the equation is, this will boil down to potassium carbonate. Remember, carbonate is polyatomic ion with a group of, with an overall charge of negative what? -2. Where is the 2 coming from? Calcium is in group 1, carbonate is a polyatomic ion with an overall charge of negative. So if I bring down that, the 2 is coming from carbonate. This is solid. Plus now liquid H2O, which is common for metal hydrogen carbonate, plus CO2. This is gas. The last two product from the metal hydrogen carbonate is constant, and you are expected to also balance the equation. Once you write the correct formulas for your product, you need to balance the equation for hydrogen carbonate. 1 potassium, 2 potassium, so it's 2 to balance out what? Potassium. So potassium and potassium are taken care of. Hydrogen here, 2 times 1 is 2 hydrogens. We have 2 hydrogens on the product side. Let's see carbon, 2 times 1, 2 carbons. On the product side, there is 1 carbon here and there is another carbon here. So carbons are taken care of. It's 1 times 2 is 2, 1 plus 1 is 2. And then oxygen, 2 times 3, that's 3, 2 times 3 is 6. I do have here 3 oxygens plus 1 is 4, plus 2 is 6. So the equation is balanced, and right now the coefficient here is 1. There is 1 right there. There is 1 right there. There is 1 right there. So the equation is balanced. Of importance is the decomposition of metal hydrogen carbonate. Learn these two types of decomposition: metal hydrogen carbonate, and this is hydrogen carbonate formula. And the decomposition of metal carbonate. Carbonate is C2. You need to keep track of this. This is what we learn in chapter 2. Please go back again and memorize that. I don't want to rush. And some I've received requests to extend quiz 2 so that you slowly, all right, study out of it. It's never too late. All right, don't let this thing just pile up. Don't let it pile up. The semester is rolling very fast, you know. Can you believe next week we're talking about like we are ending the semester next month? Please study every day. So that's what you need to know as far as the decomposition reaction, metal hydrogen carbonate and metal carbonate. Let's look at the combustion reaction. Combustion reaction, and I think here burning, you know, combustion involve oxygen, right? Combustion reaction involve reaction with oxygen, and here is oxygen gas in the air. Remember, oxygen gas, it is diatomic. It is diatomic. This means you're gonna use O2 in combustion reaction, and in particular, the type of combustion reaction involve hydrocarbon, burning of hydrocarbon. Hydrocarbons are those compounds which contain primarily carbon and hydrogen. And they always produce two compounds. Hydrocarbons produce two compounds. And these are not the only, by the way, these are not only the combustion reaction you need to say, oh, combustion is only hydrocarbon. No, there's combustion involving burning other substances or elements or compounds in air, but of particular here is hydrocarbon. They produce CO2 and liquid H2O, and you are expected to what? To balance the equation. You are expected to balance the equation. See, this is propane, naming of organic compound, 3 carbons. If you look at this equation, oxygen is involved. This is an hydrocarbon. It contains carbon and hydrogen, and you end up with only two compounds. This is carbon dioxide and H2O. Please remember to balance the equation in all these types of reaction. Remember to balance the equation in all these types of reaction. Let's see, here is example which covers decomposition reaction. A is decomposition reaction. This is combustion reaction, produce carbon dioxide and oxygen, and it involves burning of, I only forget to put the symbol here, means it's burn. This is ethylene, hydrocarbon, and this is combination reaction. I think I did this. I think I did the last one. You can look at the previous, I think there was a previous example on that. Right here, I did C. Look at C. It is exact as what you see on my whiteboard. You know the coefficient for C. Coming back to now the A, I'm going to show you how A is balanced. I know there is lead. At the outset, you are expected to know that there is lead 2 and there is lead 4, positive 4. If you don't know, then chances are you not know which one you are dealing with. You will use the compound, I mean, you will use the element which compounds with that any of those to form and predict which cation you are dealing with. For example, in A, I see that there is no substitute for wherever or two, and at the outset, carbonate has an overall charge of -2. So I know this is layer 2. So if I know layer 2, all right, I know layer 2, that means I just have to go back and forth that we have one layer here, we have one layer. How many carbons? We have one, so it's taken care of. Oxygens, 3, so it's 1, and it is 1. Sometimes it turns out that it's 1, 1. When I was taking these courses, I'll try different numbers that, and then I get stuck because the equation was balanced already. And somebody will try to say, oh, I think I need to put a 2 somewhere. I saw, no. Chances are you may also be given a balanced equation. It's okay. So long as you know what you are looking for, maybe the rules will be fine. Now, the second one is the combustion reaction. You go back and forth. Here we have what? We have 2 carbons. We have 1 carbon on the product side. So I need that 2 in front of carbon dioxide. Product side, 2 carbons, 2 carbons. 4 hydrogens, we have 2. So I need a 2 in front of H2O. So that 4 hydrogens, 4 hydrogens. And then here, oxygens, we have 2. On the reactant side, 2 oxygens. But on the product side, 2 times 2 is 4. So you want to write 4 first. And then plus 2. So we have 6 in total. We have 6 oxygens in on the product side. So we have 6 oxygens, all right, on the product side. How or what we need to multiply by 2 to make 6? Obviously, this is 3. Start with math. So if I insert the numbers, this is 1, and the equation is balanced. The equation is balanced. I think we did this before. This was 2, all right, and this was 2, and I think this was 3. 2 elements, 2 elements. 6 carbons, 6 carbons, and the equation is balanced. That's how to balance the equation. This time round, you are given, chemical formulas in the equation. Sometimes it might be worded, like you have to translate a worded chemical equation to formulas and then you balance out. I will just clear this screen here and take any question you may have on the patterns of chemical reaction. Any question on patterns of chemical reaction? Any question? If there's no question, let's just look at the formula weight. It is simple concept. We looked at this in chapter 2. Formula weight, it is used to refer to, this is 3.3 by the way, not 3.2. The sum of all atomic masses of elements to give the formula, sum of atomic weights of elements of the table. All right. If we have here oxygen and hydrogen, you'll see 1.0079, and 1, and then carbon oxygen here, the 15.99. I'm just picking up these numbers from the of the periodic table. Oxygen is number 8 here. These are atomic masses. You remember how I walk you through how to interpret. So if you are asked to find the molar mass, we talked about the molecular weight. Molecular weight and formula weight, same concept. Formula weight for ionic compound. If I'm referring to this, I would say formula weight. This, you talk about the formula weight. But it's the same concept using the periodic table. I don't expect you to memorize this, but yours is to add so that for this, you end up with 18.02 grams, and then of course per mole, we're gonna see that, and that one 58, around 58 grams per mole, just picking up the numbers and rounding up those. It's simple, so long as you have the periodic table. Finding the formula weight of an element is pretty straightforward. And I noticed that the text, the author uses one place of decimal in. You can use any periodic table with 4 places of decimal or 4 significant figures. Still, you'll arrive at the same answer. Same unit, we cover this in chapter 2, AMU, atomic mass unit. That means 4 oxygens, 1 sulfur, and 2 hydrogens. We use AMU for that, but if we have 1 mole, you will see grams per mole, AMU for sulfuric acid. So that's what I'll ask you in the exam, that what is the formula weight. If you will be given the periodic table. Now, just like naming the compounds and writing the formulas, I may give you a chemical name for the compound and ask you to determine or calculate its formula weight. If you don't know how to, for example, here, look at the sulfuric acid. If you are not given this formula, then it's gonna be, you have to do the homework. You have to do your homework, write the correct formula for sulfuric acid before you dive into the periodic table. Otherwise, you'll get stuck here and take the wrong direction, and you not end up with the correct equation. So, the correct answer. Molecular weight refers to molecular compounds. Those compounds made up of only non-metals. You know where non-metals are? Look at this, for example. This is glucose. It's glucose. There is sucrose. This is glucose. So if I just give you glucose without actually, the formula, it's hard. I know some of you can Google out with this homework assignment to look at the formula, and then of course you have to do the what? Do the math. Do the math. Understanding how to interpret that 6 applies to carbon, not the hydrogen. The 12 does not apply to oxygen, but it applies to hydrogen. That is why you see atomic weight, AW, for atomic weight of carbon of the periodic table, atomic weight of hydrogen of the periodic table. The 12, the subscript right here, stand or represent for carbon. That's what I want you to know, where the numbers are coming from. And the molecular weight is 180.0. AMU, atomic mass unit. So formula weight and atomic weight is the same thing. You will do the same. You'll use the same approach to find for that. Now, the challenge is when you are given now the worded chemical compound and you don't know what it is, it's gonna be difficult. I'm not going to solve this because everybody knows how to use the periodic table. You should know. So for A, chromium 3, that means you gotta know the chemical symbol for chromium, and it is chromium 3, so it's gotta be positive 3. Sulfate is polyatomic ion. This is not sulfide, this is sulfate. And the correct formula for that is Cr2 is coming from sulfate. Use parentheses for polyatomic ion and the formula is for chromium 3. This is the formula for chromium 3. And then from there, it's very easy now to find the molecular weight. I will use this formula weight because it is an ionic compound. Formula weight is ionic compound. This is sulfide. We call this sulfide, IDE. This is sulfate. And then, of course, SO3 2 negative, it is sulfite, ITE. Know your polyatomic ions, know your periodic table. You know sulfide, IDE, and then sulfate, what we are talking about here, make all the difference. So if you don't know, this was chapter 2. And then phosphorus, trichloride. Again, chapter 2. Phosphorus, tri, that means you have 3 chlorine, and from here you can use the periodic table, right? You can use the periodic table. I'm not going to, solve this. I know you can use, you are capable of using the periodic table to do calculation. Then potassium permanganate, there is 1 potassium, there is 1 manganese, number 25, all right? And then for oxygen, you use the periodic table to find the molar mass of compound. Any question on the molar mass, determination of the molar mass?
Yes, I just wanted to double check and make sure that I had it clear, but when would we use grams per mole versus the AMU?
Oh, Lauren, thank you. That's a cool question. When do we use AMU and when do we use per mole, right? Now, this is the distinction between the two. You know what a mole is, right? We will come back to that first of all. Let me just, before I draw the parallel, a mole is a unit used by chemists to represent Avogadro's number of things. Avogadro's number of things. If I have 1 mole of student in my section, I have 1 mole of student. That's what it is. It's just like saying, you know, a team of players, you know how many players there are in there. A dozen of eggs, you know, a dozen, you know how many eggs there are in there. Across our pencil, 144, we're gonna come back to that. So here, a mole represents Avogadro's number of things. So when I say 1 or 18.02 AMU, atomic mass unit, and then 18.02, and this I'm referring to H2O, of course. I'm just using H2O. I'm just using H2O. In both cases, it is H2O and H2O, and then I put here, let's see, 2 grams per mole, and somebody is wondering, what is the difference between the two? Okay, the first one here, when I use AMU, right, it means I'm taking 2 hydrogens. Let's say I have a super like sensitive scale. I take 2 hydrogens and 1 oxygen, and then I put it on the scale. And that scale is gonna be in AMU. And remember, 1 AMU, by the way, Remember, one AMU represent 1.6, 6 times 10 raised to negative 24. It is a small, this is gram now, this is gram. So instead of writing 23 zeros and then writing the regular gram, it's just gonna be like a super small number. So chemistry, just like the mole, they use AMU. So when I take, or if you see AMU being used, it just represent the actual number of those elements. That we have 2 hydrogen atoms, which we cannot see with our naked eye. We have 1 oxygen atom, which we cannot have with our naked eye. If I change this AMU into grams, and then I have to use this conversion factor I do have there. So it represents just a simple. Now, when I see grams per mole, that means I'm taking these formula units, these 2 hydrogens and 1 oxygen, I'm forming a compound. And then I take now Avogadro number of these, that 1 molecule of H2O, 1 molecule of H2O, 1 molecule of H2O, until I have Avogadro number of H2O, and then it will, my scale will read what you are now familiar in the lab, that it is 0.18.02 grams per mole. And that is why you will always see that it is per mole. That means you have the 1 mole. And when we say 1 mole, that means you have Avogadro number of things you're talking about. Does that make sense, Lauren? Lauren?
So if we're doing like an equation and you're kind of, like figuring out the different elements, you would use AMU. But if you were doing something where you just wanted to see the mass like per 1 mole, then that's when you would use the grams per mole.
Grams per mole, yes. Or if it say, what is the molar mass of, what is the molar mass? So if I say molar mass, for example, here, if I say molar mass, the word molar here is derived from the word mole. And you know what a mole is, right?
Yes.
So that means you'll express this in what? In grams per what?
Grams per mole.
But when I say here now, look at the PowerPoint slide. When I say the formula, you see this form, that means the formula, which means look at the whiteboard. That means 1 phosphorus. And how many chlorines? 3. I don't take Avogadro number of these. No. So the difference is we are talking about the formula. But when they say, what is the molar mass of this? And then you are saying grams per mole. And then what is the formula weight for this? That means the formula, you are just writing, you are just taking by the face value how many you are given there. Make sense?
Yes, thank you.
Yes, so you'll see the formula weight, that means AMU. And then you'll see the molar mass. And of course, if it is multiple choice, I will not give you, or you will not see that there is a mixture of AMU in the multiple choice and grams per mole in one case, no. So formula weights, so all of them will be in AMU. Molar mass, all the multiple choice will be in grams per mole. But now if it is not stated, or if you don't have multiple choice, it is just find the formula weight of this, and that's gonna be AMU versus the molar mass. All right. Thank you for asking that. I see it is exactly 12:30, and I don't want to go beyond the scheduled time. We will start from percent composition. I know it is not a hard concept. You can read and understand that. Continue working on the homework assignment. I received on the chat room request to extend the quiz too, so that they can use. Yes, I can still make it available for you to practice, or I can assign as practice. It's not going to show. All right. Let me just okay. I will assign, for the sake of And even maybe also quiz number 1, I will reassign, but it will say practice. It will not be captured as a actual grade to affect whatever is going on in your grade book. Does that make sense? That will really help. So if you have taken the quiz 2, if you have taken quiz number or homework number 2 and 1, homework number 2 and 1, I'll assign you as practice so that you practice with that over and over until you get it. Okay. So with that, yeah, Sarah, what I was saying that some people wanted to practice with chapter 2 quiz. And what I'll do is for homework number 1 and homework number 2 and maybe homework number 3, I will assign you as practice. So let's say I'm done with homework number 1. I'm done with homework number 2 and I want to practice for the exam. I will assign you as practice. You can do as many times. It's not going to affect the grade book. That is for homework number 1 and homework number 2, which you already have or you should be completing. Now for extending quiz number 2, extend quiz number 2. Yes, I'll extend that for you to practice. Some folks say we need some more time. Now, Lauren, I hope that answers your question. Sarah, that I'll reassign you quiz assignment number 1 on mastering and MyLab as practice, not as homework, as part of practicing for midterm exam number 1. And also I'll prepare the study guide. Yes, Lauren, Lauren, you will need to know that. Yes, you need to know. You need to know when gas is used, when a gas, this chemical symbol for gas, chemical symbol for liquid, chemical symbol for solid, chemical symbol for aqueous, when it's used in chemical equation. That's what I meant, but you should know that, all right? Yes, I'll extend, Sarah, I'll extend quiz 2. And then they already completed MyLab will be made available as practice as well. It will just be like the one you did, but it will not be captured in. And by the way, I don't know if some of you noticed that the setup, I will share the screenshot on the setup for the MyLab and Mastery. It's not about penalizing you, but I want you to study. You have 2 trials for each question. So don't just do one time and then submit. Give yourself time that I click, when you do the homework, say either A or B. And then you click A and then that's not the answer. You go back again and click B, and then you'll get full credit. You have 2 trials for each question. So 2 trials for each question. If you miss it, don't go to the next, try again. That marks the end of our lecture today. I'll see you again. Thank you for tuning in. I'll look forward to seeing you on Thursday, where we will talk more about the exam. Have a great afternoon. The class is dismissed. Thank you.